In the previous lectures, we have talked about symmetric cryptography or symmetric encryption. That is, whenever we have talked about encryption, for instance, we have assumed that both the sender and the receiver share some common key which they use to encrypt their messaging. Now, in the real world, this may not be so convenient, because for every single person that you wanted to be in contact with, you would have to somehow agree on that key. Actually, if we think about it, if there was a secure way of agreeing on a key, then why not just use that way of communication to convey whatever messages you have to convey to that other person? In the real world, it does sound like symmetric cryptography doesn't make any sense. Well, in the real world, we actually do use symmetric cryptography and symmetric ciphers, but we use something else to establish the secure communications. And that something is called public key cryptography or asymmetric cryptography. The asymmetry in asymmetric cryptography comes from the fact that a different key is used to encrypt and decrypt messages. The basis of public key encryption algorithms are in mathematical operations that are very hard to reverse. These include number factorization, discrete logarithm functions, or elliptic curves. In public key cryptography, we use one of these difficult mathematical operations to establish a key pair, so one key for encrypting communications and one key for decrypting the messages. So because we're making some changes to our crypto keys, we also need to change some of our security requirements. So first, encryption keys need not be unbreakable. They just need to be resistant for at least for the time that the messages need to be kept secret. Anyway, then, why is this called public key cryptography? Well, it comes from the idea that from this chosen key pair, we have one key which is secret or private, and the other key which is public or not secret. How public key cryptography works in a nutshell is that encrypted communications do not need this pre-shared secret key, but rather, if you are person A, you can send messages to person B using B's public key. And then B, if they choose to respond, they can send that response using A's public key. And the public keys are always, well, by definition public. You can post them on the internet and they will still work. Anyone can send you a message using your public key, and only the owner of the key pair, so only the owner of the private key, can open the encrypted message. The idea is that the public keys are used for encrypting messages and the private keys are used for the decryption. Like any crypto scheme, public key cryptography does have pluses and minuses. So a good feature is that the encryption no longer requires a trusted connection to share keys, unlike symmetric cryptography. There is a problem, however, so how do you know that a public key is trustworthy? Or how do we even know whose public key we are using? So on the internet, trust is based on assuming that the key actually belongs to whoever you are sending messages to, but this is not a foolproof method. Often this trust is based on using a public key infrastructure or a PKI, which is a management system for public keys, where a trusted third party verifies someone's public key. The public key encryption system that we use in practice daily on the internet is called RSA. It's named after its creators, Ronald Rivest, Adi Shamir, and Leonard Adleman. It is a method for public key encryption based on the difficulty of factoring large prime numbers. It uses key lengths between 1024 to 4096 bits. The mathematics behind RSA are not very difficult, but it can be somewhat laborsome to produce the numbers required. The algorithm works more or less like this. We choose two prime numbers, p and q, which are not the same number, different numbers p and q, randomly and independently. Then we compute another constant, n, which is basically just p times q. Then we choose some integer e, which is between 1 and n, to which p minus 1, q minus 1 is a relative prime, and another integer d, so that d times e is divisible by p minus 1, q minus 1 if p and q are primes. There is an algorithm called the extended Euclidean algorithm that will help you figure the correct numbers. After these numbers have been selected, now the public key is e, and additionally it has a public modulus n. The secret key consists of the public modulus n and the exponent d. So therefore the public key would be e modulus n, and the secret key would be n to the power of d. After computing the keys, the RSA encryption algorithm works as follows. So your ciphertext is the message to the power of e modulo n. Decryption works in reverse. So your plaintext message is the ciphertext to the power of d modulo n. Now, just in case you're not a walking pocket calculator, let's take a very simplified example of how this mathematics would work. So first we must determine some message and a character encoding for our messages. So let's choose a very simple character encoding to transform letters to numbers. Let's use A is going to be 1, B is going to be 2, C is going to be 3, and so on. Let's also define a message that we want to encrypt. So let's suppose we've stayed at a hotel and we want to send the hotel feedback, but our messages would be encrypted. So let's send a message with some feedback regarding the breakfast in the hotel. So let's say our message is going to be bad chef. Using this encoding scheme, we can quickly figure out what the corresponding numeric values for the letters are. So B becomes a 2, A becomes a 1, D becomes a 4, and so on and so on. Then, in order to encrypt the message, we must do some key computation. Now, I will skip the part where we figure out the keys because that's not core content of this course. I will leave it as an exercise to the viewer to figure out the key computation. But let's choose, for example, these are just some numbers that will work. So let's choose a modulus n that's going to be 10, an exponent e which is going to be 3, and a secret exponent d which is going to be 3 as well. Now notice that E and D are both 3, but they really do not have to be. They just happen to be in this example, but of course the public exponent and the secret exponent can have different values as well. This is just because these are very low numbers and very simple numbers. In reality, we would use numbers that are 1024 to 4096 bits long. To encrypt our data, we simply follow the encryption algorithm. So step 1 of the encryption algorithm is to raise the message to the power of e. So for the letter B, which has the numeric equivalent of 2, 2 to the power of 3 is 8. Then for the next letter A, which corresponds to a 1, 1 to the power of 3 is still 1. For D, 4 to the power of 3 is 64, 3 to the power of 3 is 27, 8 to the power of 3 is 512, 5 to the power of 3 is 125, and 6 to the power of 3 is 216. Then we finalize the encryption algorithm by taking the modulo operator. So we divide by n and take the remainder. So in this case, for B, we had 8 divided by 10 and take the remainder. Well, that's still 8. 1 divided by 10, the remainder is still 1. 64 divided by 10 and take the remainder, that's 4. 27 divided by 10, take the remainder is 7, and so on and so on. Finally, we simply use the same encoding that we started out with to produce a letter equivalent of our secret message. As you can see, it's not very well encrypted. Some of the letters have not actually changed, but you get the idea. It's no longer the same message. It is an encrypted version. It's just that our encoding scheme and our keys are too simplistic for this to make much of an effect. But you can see some of the letters have indeed changed. Decryption works in reverse. So the first step was to raise the message to the power of 3. So for instance, 8 to the power of 3 is 512, 1 to the power of 3 is 1, 4 to the power of 3 is 64, and so on. Then we perform the modulo operation again using n. So 512 divided by 10 and take the remainder, we get 2, and 2 corresponded with the letter of B. The same works with 1 divided by 10, take the remainder, that's 1, and that corresponded with A. And 64 divided by 10, take the remainder, you have 4, and 4 corresponded with the letter of D. And repeating this process, you will get the original message back. So public key cryptography is a great way of communicating with people that you don't necessarily know beforehand, because you do not have to do any key exchange before communication takes place, and that's a great thing. But it turns out public key cryptography can also be used for something else. It can also be used to ensure message integrity, and also it can be used to ensure message authenticity. So this is where digital signatures come into play. So a digital signature aims to ensure the integrity and authenticity of a message. It uses message authentication codes to ensure that the message has not been altered during transmission or storage. And it uses a public key encryption to authenticate the sender and receiver. So how does this work in practice? So digital signatures are pretty much like analog signatures. We have to be able to either create a signature for a certain message, or if we receive a message with a signature, we must be able to verify that signature. Creating a signature for a message is not that hard. There are 3 steps to the process. First, we compute a message digest or a hash using a hash algorithm. Then we encrypt this hash value by using the sender's secret key. Finally, the encrypted hash is now the message's signature. To verify a signature, you first start by computing the hash value or message digest using the same algorithm as the sender. Then you take the signature of the message and decrypt it with the sender's public key. Finally, compare the decrypted signature with the self-computed message digest. If the hash value or digest and the decrypted signature are identical, the message is original and it was sent by whoever owns that public key. This is because only the owner of the key pair can encrypt the hash so that it can be decrypted using the public key.